Semiconductors are crucial components in modern electronic devices, serving as the foundation for integrated circuits, ICs, and electronic systems. They are materials with electrical conductivity between that of conductors, such as metals, and insulators, such as glass. The ability to manipulate the conductivity of semiconductors make them indispensable in various applications, ranging from microprocessors and memory chips to solar cells and light-emitting diodes, LEDs. Now, let's look at some properties of semiconductors. Semiconductors possess unique properties that distinguish them from conductors and insulators. Key properties include band gap. Semiconductors have a band gap, which is the energy difference between the valence band, where electrons are bound, and the conduction band, where electrons can move freely. This band gap determines the electrical conductivity of the material. Doping. The conductivity of semiconductors can be altered through a process called doping, where impurities are intentionally introduced into the crystal lattice. Doping with donor impurities increases conductivity, that is the N-type doping, while doping with acceptor impurities decreases conductivity, that is the P-type doping. Temperature dependence. The conductivity of semiconductors is highly temperature dependent. As temperature increases, the conductivity typically increases due to greater thermal energy, enabling more electrons to transition from the valence band to the conduction band. Types of semiconductors. Semiconductors can be classified into two main types based on their conductivity. Intrinsic semiconductors. These are pure semiconductor materials, example, silicon and germanium, with no intentional impurities. The conductivity of intrinsic semiconductors arises from thermal excitation, where some electrons gain enough energy to move into the conduction band, creating electron-hole pairs. Second, extrinsic semiconductors. Extrinsic semiconductors are doped with specific impurities to modify their conductivity. There are two types of extrinsic semiconductors. N-type semiconductors, doped with donor impurities, example, phosphorus and arsenic, that introduce excess electrons into the crystal lattice. P-type semiconductors, doped with acceptor impurities, example, boron and aluminium, that create electron deficiencies or holes in the crystal lattice. Let's talk about semiconductor devices. Semiconductors form the basis for a wide range of electronic devices, including diodes. Semiconductor devices that allow current to flow in one direction only. They find applications in rectification, signal modulation, and voltage regulation. Transistors. These are fundamental building blocks of modern electronics. Transistors amplify or switch electronic signals and are essential components in amplifiers, digital circuits, and microprocessors. Integrated circuits, ICs. ICs, also known as microchips, consist of interconnected semiconductor components fabricated on a single substrate. They can contain millions to billions of transistors and are the backbone of electronic devices such as computers, smartphones, and Internet of Things devices. Light-emitting diodes, LEDs. These are semiconductor devices that emit light when an electric current passes through them. LEDs are widely used in displays, lighting, and automotive applications due to their energy efficiency and longevity. Semiconductor manufacturing. The manufacturing of semiconductors involves intricate processes conducted in specialized facilities known as fabrication plants or fabs. Key steps in semiconductor manufacturing include crystal growth. Semiconductor crystals are grown using methods such as the Krauss process or epitaxial growth to produce large high-quality ingots. Wafer fabrication. The semiconductor wafer undergoes a series of processes including doping, oxidation, lithography, etching, and deposition to create the desired patterns and structures. Assembly and packaging. Once the individual chips are fabricated on the wafer, they are separated, tested, and assembled into packages suitable for integration into electronic devices. Let's look at emerging trends and the future outlook. Miniaturization. Continued efforts are being made to shrink the size of semiconductor components, leading to the advancements such as nanoscale transistors and 3D integrated circuits. Optoelectronics. Integration of optical components with traditional semiconductor devices is opening new possibilities in data communication, sensing, and display technologies. Wide bandgap semiconductors. Materials such as gallium nitride and silicon carbide offer superior performance characteristics compared to traditional silicon in power electronics and high-frequency applications. Quantum computing. Semiconductors are integral to the development of quantum computing platforms, which promise revolutionary capabilities in solving complex problems beyond the reach of classical computers. In conclusion, semiconductors play a vital role in driving technological innovation across various industries. With outgoing advancements in materials, manufacturing techniques, and device architectures, the future of semiconductors holds immense promise for enabling next-generation electronics and transformative applications.